scientists for their generous support for sponsoring these seminar series. Without them, this would not be possible. I'd like to introduce Vijay, who I think I know quite well for several years, from '93 onwards when I came to do my Ph.D. So he works a lot in the area of robotics, as most of you know, and significant a lot of work has been in network multi-rotor systems. And what else can I say? Tons of publications in this area. He has received numerous awards, and he's very, very active in the robotics community, and I'm sure you have run across him in one form or the other, conferences or stuff like that. So he has received the presidential investigator award, and as I said, it's a lot of awards. So with that, I'll give the floor to him to give the exciting talk.
Thank you. I have to say, I have more J-Day stories than he has about me, so that's why I didn't open this. So it's a real pleasure to be here. I was here in 2009, so I tried to sort of find a set of things that I could talk about that wouldn't overlap in my previous talk. And so I decided to focus on some recent work that my students and I have done on autonomous flight and micro UAVs. Particularly since I think Maryland is one of the places where people are developing small UAVs and small structures that are capable of autonomous operation eventually. And I'd like to tell you some of the challenges which are not associated with the fabrication, but really in the control and the planning and the autonomy end of things. And someday, I think, the efforts to build small systems and the effort to sort of make them autonomous, they'll come together, right? So this is sort of the hope. And I'll start with a slide that actually also dates back to Maryland. This is actually from Daryl Pine from back in the days when he was at DARPA, where he started this program called nano air vehicles. And so nano in the air vehicles business, of course, doesn't necessarily refer to nanometer scale. So if you look at the UAV classification, so micro is in the range of so several hundreds of grams, and then mini is bigger and so on. If you look at this classification, most operational vehicles at this end, so the medium and high altitude, really big UAVs, and they tend not to be autonomous. They're usually controlled by human operators, oftentimes several human operators per vehicle. And so what the researchers are trying to do is to actually build smaller vehicles where, in fact, it is very hard to control them the way you control these bigger guys. But then there are challenges to make these autonomous. So I've just stuck in here some of the vehicles that we operate with. So we use off-the-shelf platforms that then we modify for our own work. We work with a company in Germany called Ascending Technologies. And so they make a class of UAVs in the range of between 500 grams to 1 kilo. So a lot of what I'm going to talk about is actually based on the Hummingbird platform, which is, like I said, 500 grams, about half a meter in diameter, about 50 centimeters in height, and which consumes about between 70 to 90 watts of power. So relatively speaking, it's small. And one of the things I'd like to point out is as you scale things down here, as is well known, mass goes as length cubed. Moments of inertia go as L to the fifth. And so if you want things that are highly maneuverable, scaling down L makes sense. And it turns out that the angular acceleration that you can get actually scales down as L, or scales up as L, 1 over L squared. So as you make things really small, you can get things to really maneuver quickly. And that's really what we're trying to leverage when we build these autonomous vehicles at a smaller scale. So we're not the only ones to try to do autonomous micro helicopters. And this is just a sampling of some of the work that's out there. Peter Beal at Stanford, his claim to fame is that he made helicopters fly and do all kinds of acrobatics by using iterative learning techniques where essentially with a model that's very coarse, he was able to iterate on feed-forward trajectories, feed-forward parameters to perform a range of acrobatics. So and I encourage you to go on YouTube, there's lots of videos, it's really impressive work. This work is from Ralph Andrea's group, where basically, again, it's a similar flavor, except they use, again, feed-forward controls to figure out how to do triple flips in midair. This work was done first at Stanford and then at Berkeley by Claire Tomlin, where essentially they use linearized controllers and then reachability analysis techniques to figure out the basins of attraction for these controllers to do things like backflips. So these three pieces of work actually focus on aerial aerobatics. Not necessarily at the smaller scale, but still nevertheless about how to use the dynamics in a very aggressive way to do complicated maneuvers. So the work that's really pushed this in the direction of small UAVs and complete autonomy is this work at ETH Zurich, where they've done vision-based stabilization, very, very small IMUs, coaxial rotorcrafts with just one camera and an IMU. And these are really small at the 50 to 100 grams range. Not very capable, but really the first step in that direction. So one of the things we've done is hire David Scaramuzzo, who's now a postdoc with us, and so we're trying to push that work too. So what I'd like to do is tell you about our work, which kind of builds on this, and I wanted to hit on three things. First, how do you control these vehicles in complex three-dimensional environments? And so the first piece of the work ignores what I think is a really hard part, which is perception. And the second piece, actually, we'll talk about how we do perception and why the kinds of controls we need and the kinds of perception we're able to do actually creates a gap, a huge gap, which we're trying to fill now. Then lastly, I want to talk a little bit about how to overcome the limitations of small rotorcrafts like this. And one of the limitations is its ability to carry large payloads. And so if your payload restricted, one way of overcoming that is to get a lot of these guys to actually cooperatively transport things. And so I'll say a little bit about that. So those are sort of three things I'd like to hit on in this presentation. I do want to acknowledge my students who have done all the work here. So the three Ph.D. students are really primarily responsible for this work: Daniel Nunge, Quentin Lency, and Frank Shen. All Ph.D. students. Mike Shonin and Christine Kathleen are both undergraduates, and Nathan Michael, a former Ph.D. student, and now he's a research faculty at Penn, who continues to collaborate with me. So these are the people who really did the work. Just launching into this, so what we work with mostly these quad-rotors, multi-rotor, micro UAVs, and the primary reason for that is they're incredibly agile. So again, this idea of maximizing angular acceleration, so this is sort of the optimal geometry, I think. You can put more rotors on and make it a little more complicated, but this is really a great geometry to work with. And so again, these are 500-gram rotorcrafts with about 80 to 90 watts of power consumption. We use these with a motion capture system. We use a Vicon system, 16 4-megapixel cameras that look down at this rotorcraft and provide state information at up to 300 hertz if you wanted to. So what you see here is examples of kinds of things we can do where we basically are able to run this through narrow gaps. We generate these trajectories automatically, and these trajectories are executed onboard computation, again, autonomously. Of course, the perception problem is trivialized because we have really good state feedback. And this allows us to generate trajectories with errors which are less than 1 degree in pitch, incredibly accurate trajectories, and plus or minus 2 inches in terms of what happened here. I can't believe this. I thought this was a Mac and these things don't happen. True. And actually, as I was showing Sarah, I have some videos of ants in this presentation. And so, there are bugs in the presentation. Sorry about that. actually, I think maybe there are too many videos here, so. So anyway, as I was telling you, so the first, there are two chapters to the story. The first chapter is one that really relies on good state information from external sensors. The second part, what we're going to do is relax that assumption and go to onboard sensing. And again, you'll see the gap between those two stories. And we hope to complete the story by bringing in a chapter in the middle that bridges the two pieces. Just a little bit about how we do these experiments. So again, here's the same robot. Now it's equipped with a gripper, which is actually a mean-looking claw. I'll say more about that. And so everything that you see here is actually computed on a MATLAB, running on a MacBook very similar to mine. We use a bridge to a middleware called ROS, Robot Operating System. And so this bridge allows us to connect heterogeneous devices like this Vicon system, interfaces to the onboard high-level processor through a Zigbee type serial interface. And you'll see that updates here come at the order of between 200 and 300 hertz, but we only do the computations at about 100 hertz. But things happen on board at much higher rate. At the low level, it happens at 1,000 hertz, and this high level processor happens about 100 hertz. So what I'd like to do is to tell you how we generate trajectories automatically, and then how we control to follow these trajectories. So some of this is sort of a tutorial, so perhaps starting graduate students will appreciate this. In order to solve this problem, you have to understand the dynamics. So here's a very simple picture. I have an inertial frame and a body fixed frame. And I have 4 rotors. The pairs of rotors spin in opposite directions. So this one, positive rotation here is counterclockwise looking down. Here, the positive rotation is clockwise looking down. And the pitches are reversed so that when all of these are spinning at the same speed, you can actually get hover-like conditions. So what we'd like to do is to control the position and the yaw of the vehicle. So there are 3 variables here and 1 variable here that you'd like to control. And so those are your outputs if you look at it as a control system. The inputs are actually roll and pitch implicitly, but explicitly it's omega 1, omega 2, omega 3, and omega 4. And by changing the omegas, you can change the lift at each of the props, and you can also change the drag, where these 2 are drag coefficients. And if you can figure out what omega 1, omega 2, omega 3, and omega 4 are for this problem, then essentially you've basically solved the controls problem. So what we'd like to do is remember this is a nonlinear problem, and what we'd like to do is synthesize a control that automatically generates these 4 inputs. So how do I do that? So again, if you write down the equations of motion, the first set of equations are just Newton's laws, which basically say that the acceleration is proportional to, well, there's an offset here which is due to gravity, and then has to do with the net thrust that you're getting from all the props. And gamma here is just a function of the drag coefficient of the mass. The second set of equations come from Euler, and so these are the angular pieces, where again, so this is the moment of inertia times angular acceleration. This is the cross terms having to do with the angular velocities. And then the alphas and the betas here are again coming from the drag coefficient, the dimensions of the machine. The important thing to remember here is that if I look at these equations, there are only 7 parameters that I need to worry about. The 3 inertias, these 3 parameters, 6, and then the motor constants, which I haven't listed here. But so if you know what those 7 parameters are, you can approach this nonlinear control problem in a very, very formal way and try to solve that, which is exactly what we did. So to give you some intuition as to how we do this, I just want to remind you that if you look at the combination of the omegas, in fact, if you just sum them up, that gives you the net thrust. So you can control the force in this body fixed frame. So the robot is tilted, you can control the force along the local z-axis. A different linear combination of the omegas allows you to control the body fixed moments. So the moments about Bx, By, and Bz. And so the real problem then is that if I have a trajectory, which is given here in the space of translations, R3, and SO2, which is the yaw piece, what should the moments be and what should the net force be in order to track that trajectory? So you'd like these errors to go to 0. You'd like to drive the position error to 0, the yaw error to 0. But to do this, you can't really formulate it on this space because this only has the translation and the yaw. You also want to factor in the roll and pitch. And so you really have to talk about control on the bigger manifold of all positions and all orientations called SE3, which is a special Euclidean group in 3 dimensions. And so here's the idea about you going about designing such a controller. So you're given this controller, you're given this trajectory, which is, again, the position and the yaw angle as a function of time, and you want to follow it. So if your very first class in controls, if you're given a linear problem, what do you try and do? Well, you try to derive some sort of a proportional derivative feedback law to follow that. And that's the intuition here. So you want the total thrust to be a function of the position error and the velocity error. This is a feed-forward term that tells you what the desired acceleration is. And then this last term compensates for gravity. Okay? So if I can actuate this in all directions, the problem is solved. And the difficulty is I cannot. The best I can do is really actuate it in a direction. So this is t, and that's the t vector. The best I can do is actuate it in that direction because all the rotors are pointing in that direction. So what I do is just project this t vector along Bz. So I do the best possible job I can. Okay? So it doesn't guarantee that the errors will go to 0, but this is the best I can do. Then the second thing we do is to try to rotate B sub z so that it moves along t. So if I do that, then a combination of finding the right projection and a combination of rotating pz along t essentially does what I want to do intuitively. So we determine what the desired orientation is using 2 pieces of information. First, the fact that I want to point along t. Second, the fact that I want the yaw to be the specified yaw. So if I combine both of those things, it turns out you can find R desired. And if I know what R desired is, I can compare the desired rotation to the actual rotation. And so here things get a little ugly because to compare 2 rotation matrices is hard. So I use a well-known result on which you know from studying the special orthogonal group in 3 dimensions, which is if you take the R desired transpose times R, and then you take the log operation on SO3, you basically get the desired, the error between those 2 things. So you get the error in rotation, and then you differentiate that, you get the error in velocity. And I don't have the expression for that. But then the rest of it is simple. It's similar to that. I take the proportional error, and I take the proportional term corresponding to the velocity error. And then I multiply by I compensate for omega cross I omega, and that's what I want the moments to be. So essentially these 2 quantities, the body fixed force and the body fixed moment, are my two sets of inputs, which I then have the quadrotor follow. So when I command that, the resulting controller that I get actually has a fairly large basin of attraction. So all these videos you see, the basin of attraction is almost, looks like it is completely all possible orientations and all possible positions. But in reality, mathematically, if you derive the basin of attraction, it turns out to be almost everywhere. So this basically says that you can converge from every point except a point that is directly opposed to where you want to be. So if I want to be here, and if I'm exactly the opposite way, then I cannot converge from that point. But that's only one point. So there's an almost everywhere convergence result, which is very powerful. The second thing is that, this is going to be a long talk. The second thing that, it's never happened to me, trust me. I hope you believe me here. The second thing about this is that, that if you look at the angular error, the orientation velocity error, the angular velocity error that you can tolerate, that actually turns out to be directly determined by how large your robot is. And I just want to show you that expression because we use that to determine. So that's really the motivating factor behind making these robots really small. Let's see if I can find that slide.
So,
Yeah.
a question. So that log, right? So that is a local result.
No, the log is it's defined everywhere.
Yeah, but you're saying, no, I'm saying the desired versus the R.
It's a global thing. It works everywhere. There's no singularity in that.
Can you actually sketch one item?
Yeah. So I just wanted to show you this term here, which basically says that the initial error that you can tolerate in angular velocities is actually determined by how large your robot is. So this is the smallest eigenvalue associated with your robot inertia. So the larger the smallest eigenvalue, right, the smaller the errors you can tolerate. So small aircrafts allow you to maneuver more quickly, which is the intuition. But when you design this controller and you analyze its dynamics and the basin of attraction, that sort of pops right out.
In the picture you saw, you manipulate by hand. This one, right?
Which picture? Sorry.
The demo we just saw.
No, the trajectory. So I haven't talked about the trajectory generation.
Have you shown the trajectory you want to follow?
I will show you in a minute.
Okay.
Okay. So
because that was your problem that you studied.
Sorry?
You studied trajectory following.
Right. So what I showed you here is control. And as John says, I haven't told you how to generate the trajectory. This is the control piece.
There's no need for model predictive control?
So we don't need it.
Why?
And I'll tell you what we do to adapt to unknown dynamics.
Right.
So I told you there are 7 parameters that we don't know. We don't know very well, and those vary from robot to robot, from day to day. And so we need to adapt to that. I'll tell you how to do this. So the only trickery here is that we use some Velcro to do this perching, which I should. So control theory doesn't do that. So how do I specify the trajectory? So I assume here that I know the trajectory. So this can be very complicated, but we choose the simplest possible way to solve this problem. And the key observation is that if you take the position and the yaw that is specified to you, and so that's the XYZ, and then the yaw we're calling psi. Any state and input variables that I need. So remember, the state is all positions, all velocities, all accelerations, possibly. The inputs are forces, moments, and so on. So it turns out that these are just algebraic functions of x, y, z, and psi, the independent trajectory variables, and their derivatives. So any variable of interest that you can come up with, I will write an equation involving derivatives and involving only these 4 variables, x, y, z, and psi. Right? So this property, to people who know the literature, is often called differential flatness. But intuitively, all this is saying is, if I have these 4 variables, and if I differentiate this, it's clear that I can get velocity from r, acceleration from r by just differentiating it. What is not immediately obvious is that I can also get the rotation matrix by differentiating it as a function of acceleration and a function of yaw. And by differentiating further, I can get the angular velocity and then the angular acceleration. So any variable of interest I can get by just differentiating this as many times as I want. So that's the key idea. So any constraint that I have, such as, I have this window that I want to fly through, angular rates that I don't want to exceed, turns out, 300 degrees per second is the max. So all those things get buried into constraints as a function of x, y, z, and psi and their derivatives.
What happens to uncertainties?
Which uncertainty?
I look at the window, it's fuzzy. If I differentiate, what do I do?
Okay, so here, perception is solved. So okay. I know exactly where everything is, and I'll tell you how we iterate on small uncertainties in a minute. Okay. So here's a trajectory problem, a planning problem. So I know what this is, right? This is, somebody told me I need to go through this window. I parameterize it using polynomials, and I'll tell you what these polynomials are in a minute. I discretize this trajectory, okay? So what we really want to do, I would argue, is that you want to find a trajectory that minimizes the snap. So for those of you who don't know, position, velocity, then comes acceleration when you differentiate it. Differentiate again, it's a jerk. And then differentiate that again, you get snap. And if you really wanted to, you can go to crackle and pop, the higher order derivative. But we don't do that yet. So I'll show you, right now what I'm going to show you is just this fourth order derivative. So this gives you a smoothness up to the fourth order, which is really what you need if you have dynamics with fourth order differential equations that are embedded, as is the case for these guys. So your relative degree of freedom for the control system is 4, and this is why we find trajectories that minimize the snap. So then you have all these constraints, and some of these can be nonlinear, and basically what we do is at these points, we linearize these constraints. And so then you're minimizing something that's a function of these Ri and psi. You have all these constraints thrown in, and that turns out to be a quadratic program, which you can solve in real time, and that's how these robots generate the trajectories. So again, if I know the environment, I know what the I know what the endpoints are and what I need to avoid, then I can find a trajectory of this form to follow using this type of an approach.
Is this offline?
Sorry?
Is this offline currently?
It's done on the laptop, and
But not on the vehicle.
No, on the vehicle only the embedded control is done.
Okay.
But you change things, and the laptop will compute it automatically, and immediately the experiment is run. And it turns out that if you look at these minimum snap trajectories, these are polarometric trajectories that have interesting time scaling and spatial scaling properties. So you can stretch a trajectory, you can translate the trajectory, and you can rotate it and do things like that, which means you don't have to solve this every time. So let me show you some minimum snap trajectories. So this is an example of a trajectory that will go from here to here, applying to that one waypoint. So here, centrifugal accelerations you generate are centrifugal accelerations are of the order of 1.5 Gs. And we can take waypoints that are time varying, like the hoop being thrown here. Right? So these trajectories are generated.
We developed a method for generating trajectories to optimally fly through any number of waypoints.
So this is what we do for our sponsors. We go through hoops, jump through. But again, just to show you that you can have multiple waypoints, and you can fly through those. And so then comes the question: well, can you really do these kinds of trajectories using the approach that I showed you? And the answer is not. It's not immediately applicable. And the reason is the passing through this requires very, very tight controls on pitch and roll. And so what we have to do is actually piece together different trajectories. And we designed different trajectories, and we spliced it together, again, in a semi-automated way. And people who know, the mode switching literature, it's the third time in a row, will know. I shouldn't have showed you all those videos. I bet that was the end. So what we do is we have a controller that generates trajectories, and then we have another specialized controller that ignores the position part and just focuses on the yaw and the roll and the pitch. So if I accelerate, get momentum, and then I can just flip my body and then get through that window, I can then recover using a trajectory controller. So we essentially piece these things together in this work. Do you have questions about this? I'm going to shift gears.
When you piece the trajectories together, right? Is there a discontinuity or possible instability problem at all?
No. So so we're looking at the snap variable and to make sure that everything is continuous, is C3 continuous in compass.
Even when you switch?
Yeah.
Okay, thank you.
Last one.
Please.
Okay, it's very clear how do you specify X, Y, Z, but how do you specify U? You can specify various time histories of U, right?
So, but that's what I was trying to show you, that if you tell me what X, Y, Z, and psi you need as a function of time.
I don't know psi.
Hmm?
I but you don't know psi.
Okay, good. So if you don't know psi, it'll find the best possible psi that optimizes that function. Right? So this is a two-point boundary value problem, and if I start off with some psi and I say I want to go to this psi, it'll find the best possible sequence. If you don't specify the endpoint, it'll just find the smoothest trajectory, which for this particular case, if you don't specify this, it'll just keep that same orientation.
So if we go to collaborative control, I don't know if you're going to go there, but then, right, I am going to tell you the trajectory in real time, and that's why I'm asking this question again and again. Can you compute it on boards?
So we're getting to the point that for this machine we cannot. For the other one that I'll show you, we can.
And in particular, as you go to smaller vehicles that we're interested, right, that's going to become an issue.
Yes. Yes. So you asked about the question. So what if you don't know the parameters? And so no matter how much modeling you do and how much theory you do, as I think it was Yogi Berra that said, the theory and theory are not the same. In practice, they are. No, the other way around. But anyway, so you have to do some adaptation, and this just gives you. So this is the kind of thing you want to do. So you hover, you accelerate, pick up momentum, you just change the orientation, and then you switch back either to hover or back to trajectory control. So when you splice these things together, the key variable is what set points do you use and when do you actually transition from one mode to another. And that we learned. So for the problem of going through the window, in 7 iterations, we got the right pitch angle. So you're just iterating on a few parameters, and it turns out that although you can't prove it in practice, all these trajectories converge pretty quickly to the ones that you want. So let me move to the next piece, which is can I do everything on board? So to do everything on board, you need a little bit more computing, you need a little bit more sensing. So this is a bigger vehicle. It's about 1 kilo in mass. And it has on board a monocular camera. It has a laser range finder, a local view, which has up to 30-meter range. And then it has basically a netbook processor on board. And so we'd like to do similar things without the Bicon system now. And I want to tell you how we do this at a very high level. So this is sort of the block diagram that shows how different modules interact. The most important thing about this is this left-hand side. So these are the 3 sensors that we have. An IMU that tells us what velocities and accelerations are, roughly 100 hertz. We have laser scans, and these are 2D laser scans coming in at 40 hertz. We have some mirrors that are arranged that basically allow us to get reflections from the top and the bottom. And then we have imagery that comes in at 2 hertz. And remember, you're doing everything on a 1.6 gigahertz processor, so you really cannot crunch on imagery in real time. You just don't have the oomph to do this. So if you look at that netbook processor, 30% of its work is just spent on getting odometry information, which is this sort of first block. So what this does is it looks at the laser scans, and it looks at incremental motion as predicted by the IMU, and it matches those using a technique called ICP. And this takes about 20 to 30% of the CPU, and at the end, what you get is 6 degree of freedom odometry in the sense that at every time step, you get a sense of how much you've moved in XYZ position, roll, and roll, pitch, and yaw. Then the second thing we do is try to now understand where we are in the environment, where we build an occupancy grid. So you divide this into a grid, 3-dimensional grid, X, Y, and Z direction, and every grid cell is either occupied or not occupied. And then you try to figure out, based after an incremental motion, if the measurements you made before are consistent with what you have now. So this technique is loosely referred to as simultaneous localization and mapping. And so incrementally, we get pose estimates. And between these two guys, you have 50% of the work that's being done, just to figure out where you are. So that Bicon system starts looking really attractive at this point, right? So half the processing is just figuring out where you are. And so the rest of it, I just want to highlight. So then loop closure is another important piece. So one of the things you do is when you go around the hallway, and let's say you do a full circle, come back, you want to recognize that you're back at the same location. Otherwise, the maps that you build have a tendency to drift. And so this sort of ensures that your maps essentially get straightened out. It's like solving a constrained optimization problem. And this is also done on board at a much slower rate. And then lastly, I want to point out that we run a control loop at 100 Hertz. And this control loop also includes an adaptive controller. It's actually a parameter tracking algorithm that basically tracks the trim parameters, the roll pitch, and the thrust that you need in order to accommodate uncertainties in aerodynamics. So one of the things, not being very familiar with this was really surprising to me is that if the robot goes from, free space on top of this table, the flight characteristics are just very different. And so this is sort of adapted, so although it doesn't know about the table, it knows it needs to be at a certain location, and if it's not, then it basically says, well, I got to add on to my thrust, and that's one parameter. These are parameters that appear linearly in the equations that the robot calculates on the fly. So all this is done without the fancy nonlinear dynamics that I showed you earlier. When you're doing all these computations, you cannot afford to have the pitch, the roll, etc., deviate significantly from the nominal hover position. And like I said, these are two stories that are somewhat disjoint and they're bookends to the real story we want to tell eventually. So this is all based on linearized dynamics. Otherwise, to do adaptive controls is very, very hard. But just to show you, so this is what you get from the errors that you get from onboard estimation. You can see the errors here are roughly twice what we get with the Vicon. And again, there's a lot of noise here because of the errors, because of the changing wind conditions. But we do a reasonably good job. And what I want to show you is a quick video of how we operate in environments like this. This is a 4-story building, and this is imagery coming from the robot. And hopefully the video won't crash again. So you take a robot, you just ask it to go inside, and it starts building a map immediately. So blue here is the ground floor, right here. As the colors get hotter, you're going higher and higher. And the robot basically plans a path. This red trajectory is what it plans based on inputs given by the human operator. So the human operator in this particular case essentially tells the robot, I want you to go here, and the red trajectory is planned in the X, Y, Z psi space. And then the robot essentially tries to follow that trajectory, and you can see the occupancy grid map that's being created online. And so this is actually fairly tricky, especially when you go through these confined environments like this, where again, the wind flow conditions change quite a bit, especially when you go upstairs. I mean, this discontinuity at every step. So this actually looks relatively simple. It's a really hard experiment to do. And we've gotten it to the point that it works really robustly if you are in sort of these 2D buildings, 2.5D buildings. So it won't work, for example, in a Frank Gehry building where there's no sense of what vertical is and all the walls are curved. But in most man-made buildings, human-made buildings, I think.
What information it has a priori?
Sorry?
What information does the vehicle have a priori?
Nothing. Nothing. It has no GPS. It has no information about the environment here. And you can see whatever it's building is right here. But it is using, and it's assuming that the world is 2.5D.
Okay.
Right. So if you
so
go into
a
canyon without a vertical, without a horizontal surface, it's going to be lost.
So it finds the obstacles and all that stuff, right?
Yeah. It does all of that. And,
so if I have a wall that is 3/4 to the ceiling, you will find the opening?
Yeah, it's not a problem. Actually, I will show you stills of pictures where you've been to Penn and you know the 3-dimensional nature. There's like mezzanines that don't extend all the way, and so these are experiments that we have run. So at an engineering complex, all the buildings are connected, but the connections are sort of piecewise continuous, right? So you go from the 2nd floor to the next building, which happens to be in the 3rd floor, and then you go to the next building that happens to be in the 2nd floor. So you have to go up and down, and it's exactly the kind of thing you're referring to. And so, but again, what the saving grace is, the walls are roughly vertical and the floors are roughly horizontal. Not true for stairs, not true for ramps, but when you have a ramp, the walls are there. And so it uses all these correlations to basically figure out where it is. So just to, so this map was actually not generated automatically. Frank Shen actually had to carry the robot through, all these different corridors and so on, not because we couldn't do it automatically, but because we don't have enough battery life to run this whole mission. And so that's a sad commentary on the state of power and battery and so on, but it's reality. So this is done, the robot was hand carried most of the way, just because we couldn't get the data.
For the two vehicles you showed, what is the actual flight time on the batteries? Do you know?
About 12 minutes.
12 minutes.
Yeah.
Okay, thank you.
Yeah.
Sorry, in the mapping you were giving it points to go from here to there, if you do the trajectory.
Yeah, so
Points.
remember what the user is seeing is really this picture, right? And so if I'm looking at this picture and let's say I'm over here, I can say, well, this area looks like I need more information, so I click on that and it generates a trajectory. And that's what I was trying to show you with the red line that sort of snaked out. So right now it's just it just went up vertically. So there's the red line. So that piece it's planning, and it's planning in this obstacle fill environment. Okay. So this is the piece we're trying to link up to that earlier piece that I told you about. So we know how to do control in really complex spaces, and we're trying to sort of catch up in terms of perception, try to figure out where we are. And if we could do this at 100 hertz, and if the robots could be really small, then those two stories could be told back to back. But right now there's a missing gap. So the last thing I want to show you is how we actually, and this is one of the things that John was asking about, so how do we actually do cooperative manipulation and transport where actually there has to be tight coordination?
One last question on the previous one.
Yes.
As you try to marry those two, and you go to smaller vehicles, and you want to do everything autonomous, and you have less computational resources, you don't anticipate there's going to be a problem of delay in the computation? That matters?
Yeah, I mean, so this is why I said we have to do it at 100 hertz. You have to have a filter that comes at 100
Remember, that's
hertz.
why I asked you in the beginning, you don't think there's going to be a benefit if you do a little bit of prediction ahead? Because if you have your sensors and you know where you want to go, you can do a little bit look ahead and then compensate for any delay you may have later on.
No question. So here we're basically saying we know nothing,
Okay.
and there's no prediction with it. In a partially known environment, I think there are tricks like this you can play. But the one thing I'll tell you is, a lot of what you're seeing is the result of working with different sensors, with different frame rates or different update rates, with different accuracies. And there's no systematic way of sort of saying, well, if I have something at 100 hertz with this kind of accuracy, something at 40 hertz with this kind of accuracy, something at 2 hertz with this sort of accuracy, how do I combine this and design a controller that runs at 100 hertz? And you would think that by now we would know how to do these, even in the linear domain, but this is actually pretty hard. And so a lot of this, I'm embarrassed to say, is just some really good engineering. Students who have amazing intuition. And I wish I could write all these equations and say this is the best way of doing it, but we can't. Let's see, I'm going to try and wrap this up in 5 minutes. Yeah. So I want to tell a story about how we do cooperative transport and cooperative assembly. So some of this is Mike Schumann's work, where we've been designing these grippers, which are these two-part epoxy resin polymers with embedded fish hooks, so you can actually grab onto things like this and perch on tree trunks, tree branches, and so on. More benign grippers are these, where you actually can pick up objects like this, and I'll tell you a little bit about construction. So these are very simple objects, very simple grippers that we can use now to pick up things and assemble things. The assembly here is achieved by snap fit fasteners, which is essentially a set of embedded magnets. So we've trivialized the assembly problem. So you'll see here that actually the robot tries to assemble, and it looks at the reaction forces it gets to figure out if it assembles things properly. So there's no perception here, except for the feedback that it gets from its own motors. But using this approach, you can actually assemble large structures pretty quickly. The only limitation, again, is how much time can you fly. And that's, we're down to 12 minutes, and it looks like I have problems other than battery issues here. Okay, so what I want to talk about in the next, 3 minutes is two types of things that we've done. One is trying to figure out how to drive robots together. And the second is how we can do construction. And so these are coordinated control experiments. Actually, I won't talk about all this. My laptop is very tired today. So this is many robots operating in concert. By the way, this is again done with the Viton system, and the only real sensing besides position and velocity is forces that the robots infer. Again, you have to run a parameter estimation loop on board to figure out if you're carrying something or not. Right. So if I pick up an object, if I heft it, I have a rough idea of what I'm carrying, and that's what these robots use to verify successful grasp, and then in this case, successful assembly.
There's no direct communication here between the robots.
No, they do. They talk to each other, but in practice...
Through where?
They actually talk to... So that's why I said in practice it's centralized because of the central laptop that's talking. So the laptop has 3 clients and each robot.
Okay.
So we can build structures like this using this approach. The one thing we are doing to ensure that we can actually carry structures that are very heavy is to figure out how we can get multiple robots to pick up big structures. And here, what the robots do is a pointwise optimization, where given a load, they figure out what's the best way to apply forces. So this turns out, if you do a pointwise optimization, it turns out to be a very simple Moore-Penrose type inverse, which actually lends itself to decentralized computation. And so that, I'll skip all of this, so I wanted to show you that you can actually manipulate the weights of the inverse to actually do this very efficiently. But I'll show you the resulting video of experiments. So this is that nasty claw that I told you about, which you can actually use to dig into 2x4s and you can actually pick it up. These claws are amazingly strong. You can pick up 1 kilo payloads with this. And so here are robots sort of cooperatively holding things together with these claws. Grasping is a little bit of a challenge, but once you grasp it, you can actually get the robots to cooperate pretty nicely. So this is the grasping experiment, and I think grasping. Yeah.
The effect of the load on the vehicle.
Yeah.
To what extent the synchrony in grasping, you see what I'm saying? If I have a beam and I'm trying to pick it up, okay, with 2 places, right, and it's heavy enough, then it's going to create a problem.
Yeah.
So how do you handle that?
So the way they handle this is, so you have to make sure that the controls, so remember the controls are, I control the net thrust that I apply and the body moments that I apply, right? And so now the question is, what body moments and thrust do you apply that are consistent with each other? So that pointwise optimization ensures that. So if you know what the load is, it's actually pretty straightforward to decentralize it. If you don't know what the load is, you run an adaptive loop locally to make sure that forces are...
You don't need to communicate between the two?
So in this case, they're only communicating to the extent that they know the task.
Okay.
And they know that if you and I were carrying an object and we were doing the wrong thing, we would feel each other's interactions.
Right, that's what I'm getting. If we do it as 2 humans, we communicate via actually our reaction with the beam, let's say.
And that's what
That's
happens.
how it happens.
Yeah, that's what happens. Yeah.
Thank you.
Yeah, that's exactly what happens. Yeah. So I think I'm living on borrowed time here, so I'm going to finish here and just talk about all these other interesting things. If I can just find my slide. So, actually, I have 2 slides to show you. So, again, so what I firmly believe is that we have the ability to create these really agile micro UAVs, and the big challenge is to 3D state estimation, as I mentioned. That takes 50% of our CPU right now, and that's a terrible thing, right? And because of these size, weight, and payload constraints, it's a challenge. If I can put all kinds of sensors on it, I can overcome that. So in fact, as we were doing this work, coincidentally, Microsoft came up with this Kinect stereo camera, and we have that on board, and it's made life a lot easier, although we don't have results from that yet. And then lastly, if your payload limited, there are lots of ways to sort of solve that by cooperation. So before I stop, I wanted to show you a clip from one of my favorite TV heroes who talks about our work.
For years, I have been warning about the threats of robots rising up against their human masters. Well, now scientists have reached a new milestone in our enslavement. Flying robots that can autonomously assemble magnetic rods into simple cube-like towers. There's no remote control here, folks. These buzzbots have a hive mind of their own, and apparently the first step to enslaving us is building dorm room shelves. Which brings me to threat number 2, flying robot drones. Folks, today they're constructing a 3-foot tower. Tomorrow, it's a sprawling prison for 3-foot prisoners. Provided they can build it before their batteries run out, and it can't be too windy. Even if they don't enslave us, they will crush us at Jenga.
All right, thank you very much.
Questions?
Yeah.
Have you tried something like a little rag doll, something to simulate like a downed individual that could be airlifted? Let's say that would be the ultimate goal. But so then one robot would be picking up an arm, the other leg, the other one, whatever.
Yeah, we've thought about sort of cooperative retrieval of victims, particularly. So it's, I think, easier to think about doing it with just recovering bodies as opposed to recovering live people, because then you don't have to worry about mutilating them or anything else. But yeah, so we have done things like similar to this. As you can imagine, when you want to ask for money, these are obvious applications that rise to the top. So. Yes.
Question about flying through the hoop that was tossed in the air.
Yeah.
So you were talking about optimization of trajectories. Was that trajectory optimized online, or how did you exactly do that?
So Daniel Ballinger is the guy who did it. So the optimization, doing it online is not the hard part. The hard part is when you throw it in, it has to take a snapshot and then predict the physics of that falling hoop. And it turns out that that falling hoop doesn't fall with acceleration with a G. And I didn't, aerodynamics turns out to be a significant thing. So you have to actually fit this model of how the hoop falls. If you don't know that, then you can't fly through it, right? So the other option is you real-time, you estimate the trajectory of the hoop and then try to fly through this. There, you can't do the calculations fast enough. Because you'd have to do the calculation 100 times a second, and that would be really hard. Yeah.
You mentioned the error that you get when you do a closed loop.
Yeah.
So what exactly how do you correct?
How do I correct?
Yeah.
So, so the idea is that if you think about this exercise yourself, like you see this, you take a picture, you see this, you take a picture, you're building a map, and then you go around, you come back to the same place. The chances are you won't come back to the same place. So this square will be more like an open loop curve. But if you see the same thing, we're smart enough to recognize, well, this is the door I saw back there, so that these two things must be aligned. So you can formulate it as a batch least squares and solve it, and that's roughly what the robots do. But how to detect that this is a place I've been there before? I mean, vision guys know how to do this, but you essentially keep a list of features, you organize them into words, And then you see, well, these are the words that I've seen before, and so I must be reading the same page that I read back then. And that's roughly how this thing works.
So, actually, could you go back to that slide with
Log. Oh, the log. You don't believe that, do you? John, did you have a question while I'm putting up that slide?
I only want to ask if anybody else doesn't have any, because I already asked too much, but if nobody else has any, ask.
Oh, yeah, I just said it. Sorry.
This log gives you a skew symmetric matrix.
I missed it.
I have a question before my
So,
Yeah. So
We didn't hear the question because of the...
So the question is,
Okay, there was
you
dynamic
can only
noise
fly
here.
for, Stephen Colbert said you can only fly for 10 minutes, what do you do? So we actually, we're not power people. We can figure out how to do things like recharging autonomously. So we're building a bank of automated charging stations. And it turns out that's not tricky. It's quite tricky because to actually get the contacts without, these are lithium polymer batteries that explode least bit of exclusion. So you really have to design this carefully. So that's our solution. So if I know where the charging stations are, I may only have 3 guys doing something at the same time, but I can have 10, and I can solve the logistics problem very easily.
So the question I want to ask is this. If I go to the dynamics and the estimation, if I reformulate everything in terms of, let's say, quaternions, right?
Yes.
Then I get a lot of advantage in many of the computations you have to do. And you can actually do special quaternion processors and do it very fast. Any thoughts on this line?
So,
I'm
whatever I did, I could do it with quaternions.
I'm trying to avoid the linearization, because I think the problem in the computation you're having is because you linearize. I may be wrong, but that's what I'm thinking.
No, the first part has no linearization.
Your control is linear. Your control is linear.
No, but I'm compensating for all the nonlinear terms.
Right.
So I'm computing the nonlinear terms. And in fact, the log thing that JJ keeps asking me about is a nonlinear computation. So this error...
Which is nonlinear?
This error signal that I compute
right.
Is actually the geodesic on SO3.
Yeah.
So it works even if your desired orientation is like that. Right? It computes these large errors. And it figures out how to take that into account and massage it in a way that you can stick in your control network. So it is a nonlinear computation. The second piece is linear, and only because we don't have the wherewithal to get it to do anything but very small excursions from this stability is just way too much. The interaction between the perception and the control loops, plus it's a pretty big thing, and I told you the smallest eigenvalue of the moment of inertia is a critical factor of how fast, how robust you are. Thank you. Yes. So if I give a point that's really far away and I've never been there, it'll try to go there, and then the minute it spots the wall, it's going to get stuck. So it has so path planning is only as good as the information that you know, and it'll get stuck. So, but in this right. So in this, what I showed you, the user is actually commanding the aircraft at a high level. But what we're also doing simultaneously is figuring out how the robot can be deployed in an exploratory mode, where essentially you can take information, you can compute the entropy associated with the information, and then all you have to do is go in directions where entropy is high. And so that way you can just automatically explore the environment. And so this works reasonably well in 2D. In 3D, for reasons I don't want to get into, it's a little more complicated practical issues, and so we haven't done that yet. But so that's one way of removing the human operator entirely. So then you just sit in your building and go tell me where everything is, and come back, and hopefully it should do that. So life is 2D. I think we can do that.
Any other questions?
I know everybody wants to go. You saw the vehicle was navigating through a building, and then the importance of the floor and the walls, was vital to that navigation. Have you tried that vehicle in kind of a wooded area?
Yeah, so we've gone from outside, our building outside with our trees, and it works reasonably well. Again, the question you should be asking is, what if there's no ceiling, and what if the land, slopes and rocks and things like that? It won't work.
But to some degree,
Unless you have trees that are
very nice. Yeah, so in some cases it might be okay, in others, then all bets are off.
Yeah. So again, it will not collide. It will not fall, but it won't be able to land.
All right, so with that, I think we'll
All right, thanks.
thank the speaker.